The experiments that we run are typically used to verify or refute certain aspects of algorithms, such as their performance or running time. And because of it, it's important to talk about modeling the performance. So when we analyze an algorithm in theory and say it runs in log n time, what we're saying is that the function in log n is a good model for the behavior of that algorithm or for the running time of that algorithm. Okay? So even things such as space or running time could be thought of as models, and that's what I call by modeling the performance. Another question is, if you have a model for the performance of the algorithm, so for example, you think that this algorithm runs in log n time, how can you verify that experimentally? Well, there are actually many ways to do it. So there are statistical tools such as regression and stuff like that, where you can actually collect some data and verify that whether the function log n is a good match for the running time that you observe in practice. In this course, we're going to do something very, very simple because I don't want you to run regression analysis and stuff like that. So what we do is that we just look with our own eyes. And so if you have a function and if you plot it, so let's say this is running time and this is the input size. If the plot looks like this, then you can say this function is a linear function because the plot of the running time looks like a straight line. Okay? But of course, what do you do with functions that are not straight lines? Well, it turns out there are lots of tricks you could do. For example, when you expect something to run in log n time, then what we can observe is that because of the law of the log, then log n should increase by constant when n doubles. Okay, so therefore, what I mean is that log of 2 times n equals log of n plus 1. Okay. So when input doubles, then the log function increases by 1. Okay. And the way you can verify this is simply by plotting the log. So this one on the log scale. If you plot like this, then the logarithm will look like a straight line because of that. Okay. And then there are similar tricks if you suspect your algorithm runs in a particular running time. So for example, if your algorithm you suspect it runs in, say, n to the alpha, if you think that this is the model for your running time, then what you can do is that you can take the log of this. So this is, let's say, t of n, which is the running time of your code. When you take a log of both sides, then log of t of n log of t of n equals, by the law of the log, so this is going to be alpha times log n plus some constant. Okay, so this is basically how it will look like. So therefore, if you plot both axes based on log scale, so this is x-axis and this is y-axis, then you should see a linear relationship because y equals alpha times x plus the constant. So therefore, it should look something like this, where this axis is log n and this axis is the time, or log of time that you observe. Okay. And the easiest way to see all these behaviors is to double your input size at every single step. And this doubling is will make sure that you'll get, when you do the log factor analysis, when you plot based on the log of the thing, you are actually essentially plotting at equal sized intervals. Okay, so essentially you're plotting at these x coordinates by doubling n at every single input. Okay. And finally, once you think you have got it, or you have nailed it, in that case, what you can do is simply do the division. Okay, so you can do something like this. If you really think that n log n is the correct answer, then you can divide the running time by n log n and then check for constant behavior. So you can do this, check for log behavior, and in this text, what I wrote is that If you're not sure about the factor alpha here, then you can do this. But if you're sure about the factor alpha, then you can divide T of n by n log n. And if your T of n is O of n log n, then this should essentially be constant. So once you plot this on the log scale, so this is log of n, what you should see is like this more or less constant function. There could be some fluctuations, but it should look more like a straight or a horizontal line. And if that's the case, then you can say that we have nailed the exact dependency of this function based on n, and it is, say, n log n. Okay. In practice, things become much more complicated because there are lower order terms that can change things. So for example, if you have a function that looks like this, then in this function, the lower order term actually dominates for small values of n. So for example, if you run this algorithm starting from, and let's say you double every single time, you start from 10, so you plot for 10, 20, 40, etc., etc., you might see some really funny things happening like this. Okay, so like at the beginning, the function might look funny. So for small values of n, you might see that the function doesn't behave well. And of course, the range that this function doesn't behave well can depend on this constant over here. So if you have a function that has very weird combinations of parameters or constants, then you should be careful about the small values of n. Because of it, it's actually a good idea to test algorithms for large values of n, because when n becomes larger, the impact of lower order terms becomes much less significant.